Today we are just going to solve some problems regarding an atmospheric pressure. So atmospheric pressure is basically air molecules that is being pushed. So the basic unit of atmospheric pressure is 1 Pascal, and it can be written in the form of newtons per square meter. And this is the units. It's 1 atmospheric pressure is equals to 101,325 pascals, and it also equals to 101,325 newtons per square meters. So that is the other units. So let's talk about the other formulas. We have mass of a fluid. So this mass is equals to the density divided by the volume. So let's just divide this. So this is the volume of our fluid. And this is our density. So we just basically derive it though, because density is mass over volume, right? And this is pressure of the fluid, and so this one is going to be the density of the fluid. We have G, that is uh, gravitational acceleration. We just define gravity for short, and we have the depth, or we can call this height. Now let's calculate this first problem. A 5 kilogram rectangular block with length of 70 centimeter and width of 40 centimeter rests on a table. What pressure does the block exert on the table? So we all know that pressure is equal to force over area. So force that is being applied here is going to be mass times acceleration, second law of motion, and the force that is being applied here is just the weight force. And the weight force is defined as mass times gravity. So our mass is 5 and our gravitational acceleration is 9.8. So basically we're not going to use some negative sign there. Just keep all simple. We're just going to keep all simple and make it positive. So the weight force that is being applied is 49 newtons. Now the area, or the area of our block, is going to be 0.7 times 0.4, right? So this centimeter, we can just write it as 70 times 10 raised to the negative 2. And 40, we can just write it as 40 times 10 raised to the negative 2. Or we can just divide this by 100, so we can transform it into meters. Okay, so the answer, so the pressure that is exerted on this table is going to be 175 pascals, or 175 newtons per square meter. Now let's try this one. A closed rectangular container where with dimensions 4 meters, 4 by 5 by 6 meters is filled with water. What is the pressure exerted by the water on the bottom force of the container? So we're just going to use this formula, the pressure of a fluid. So we have the density of the fluid, that's going to be water, so it's 1000 kilogram per cubic meters, and our gravitational acceleration is 9.8 meters per second squared, and our depth is just basically 6. So the pressure that is exerted by the water on the bottom purse of the container is just going to be 1000 times 9.8 times 6, so that's going to be 58,800 pascals. So this is the pressure. So a closed cylindrical pressure container filled with a fluid that has specific gravity of 1.7. What is pressure exerted by this fluid at a depth of 15 meter? So we're going to introduce a new formula that's going to be specific gravity is equals to the density of the object divided by the density of the water. So specific gravity is basically defined as the density of something relative to the density of another. So that is the specific gravity. So let's just abbreviate this. So it's SG is equals to P sub S all divided by P sub H2O. We're going to solve for the density of the object because we do not know that. We do not know the density of cylindrical container. So that is going to be 1700. So now we can just plug it in into our formula. So the pressure of fluid is this thing. So the density of the object is 1.7 times 10 raised to the third power. We just made it in a scientific notation. So just to make it cool, 9.8 and 15. So now we can just use our scientific calculator. So the pressure that is exerted by this fluid at a depth of 15 meters is going to be 249,900 pascals. What force is exerted by the atmosphere over an area of 10 meters, 10 by 15 meters at sea level? So we all know that pressure is equals to force over area. And we're going to calculate the force that is being applied here. So it is on the sea level. Therefore, the unit is going to be 101,325 pascals. And the area is going to be 150. Now we're just going to cross multiply this. So the force that is exerted by the atmosphere over this area is going to be 15,198. It's around a million. It's 15,198,715 newtons. So it's a lot of force, right? So now let's try this another problem. A closed rectangular box with dimension 5 by 8 by 12 is filled with air. What is the pressure exerted by the air on the bottom of the box? Density of air is 1.29 kilogram per cubic meter. So we're just going to simplify all of this problem using the equation above us. And we got this formula at last. So our densities is 1.29. And our volume is going to be 5 times 8 times 12. And our gravity is 9.8. And length times width, that's the area, it's 5 times 8. So now the pressure here is going to be... we're going to put this, all of this in our calculator. So that's going to be 151.704. That's not a thousand, that's just a point. It's a decimal. So this is 151.704 pascals. So that's the air on the bottom of the box. What is the mass of vertical column of air that exerts a pressure of 1 atm over 10 by 10 square surface? So pressure is equals to force over area. And we're going to calculate the mass. Force that is being exerted is, here is this, the weight force, and it's defined as mass times gravity. So solving for the mass, we got area times pressure. The denominator is going to be the gravity, the gravitational acceleration due to gravity. So now we're going to put what we know, that's the area. Our pressure is 1 atmospheric pressure, so we're just going to use pascals. So we got 101,325 pascals and divided by 9.8. So our mass, the mass of this vertical column is it's way big. So it's around this number. I don't know what number is that. It's around a million. So it's 1,033,000. Okay, I'm not gonna read that. It's too much. So this is the mass of the object. It's around a million kilograms. And that's basically it for this video. But I'm gonna put this at 1.